Right. Okay. Good evening, everyone. So, uh, so today I'm going to give a half hour or more than long talk on some of the research that we have been doing over this COVID break, or just before that as well. So, my talk would be in the area of neurosymbolic learning, mainly in those area where we are interested in incorporating some form of domain knowledge into deep networks. And specifically, I'll be talking about something that we have developed in the last year called bottom graph neural network, and we'll try to see how it is applicable in drug discovery, specifically generating novel small molecules. So this is a preparatory talk um, for the conference talk that I will be giving in the next few days at IJCLR 2021. Okay, so the broad problem that we are interested in is this. Um, if you know the machine learning mainly, it takes some data, there is a learner L, and it constructs the model. Now, what we are interested in is constructing model M from data as well as some background knowledge B. Uh, Now, in this talk, we are concerned with problem where the data D is relational, example graphs, and B is available in some symbolic form. It could mean that it is either available in propositional or first order logic form. L is a class of deep networks that deal with such kind of data. In terms in the relational world, call it graphs. So those kind of networks are called graph neural networks, which have recently been very popular and have been adopted in several applications, including Google Maps. Um, and M is a trained GNN model that L returns. So have been able to achieve this idea of incorporating symbolic domain knowledge into GNNs in two different ways. One is a very simple approach called Vertex and this graph neural network, BRIGANS. And this is a joint work with Professor Ashwin Srinivasan and Lokesh from TCS Research, and it is published at MLJ this year. I'm not going to talk about this because we don't have much time to talk about all the works that we have done. So I'll give a basic insight into the results only. The second work that we have done, which has been accepted recently at MLJ, is more directed inverse entanglement, using the idea of more directed inverse entanglement that is available within inductive logic programming to incorporate the symbolic domain knowledge into GNNs. And we call them BOD GNNs. And this is joint work with Professor Ashwin Srinivasan and A. Bhaskar from our department. And then we'll see a novel application of BOD GNNs for target-specific molecule generation. What does this mean? I'll come to the slide and describe it later. So what it mainly does is it uses a very nice collaborative combination of generators and a discriminator. This is a joint work with Professor Ashwin Srinivasan, Lokesh from TCS Research, and Arijit Roy from TCS Research in Hyderabad. This has been accepted at Inductive Logic Programming Conference, which is the primary conference in this area. And we'll try to see what results we have got in this. So I'm going to present all these three works during this October 25 to 27 at IJCLR, which is the newly formed conference on learning and reasoning. Okay, now data are relational. What does that mean? If you notice, many standard deep networks deal with data which are just tensors or grid-like structure, such as images or even text. They are in turn converted to some form of tensor. But many real-world applications do not deal with tensors directly. Instead, what we'll be looking at here is some representation of binary relations, which are graphs. For instance, a citation network or a molecular graph or a protein-protein interaction network, transportation network. So all over the place, there are relational data. So we're trying to look at some application of the kind of work that we have been doing for molecular graphs. Further, many real-world designs involve relational databases where the stored data are multi-relational. And this multi-relational information can also be composed from a set of other multi-relational or binary relations. So we're looking essentially at more complex data than just tensors. So in molecular science, this is a molecule. I don't know the name, how do you call that, but the corresponding molecular graph representation would be this, where each node would correspond to an atom, and each edge will correspond to a bond. So in relational representation, we will write that that molecular graph that is shown in the previous slide, that is here, given here again. In Prolog, for instance, we can write it as atom. So molecule M1 has a carbon atom at position 1. Similarly, molecule 1 has a carbon atom at position 2, and so on. And similarly, we can also write the bonds. Molecule M1 has a double bond between position 1 and position 2, and so on. Now, our works deal with symbolic domain knowledge. For molecular problems that we'll be dealing here, we have access to the facts and definition of various functional groups, such as amine, alcohol, ether, and there are at least 40 others, I guess. And rings like aromatic ring, non-aromatic rings, and heteroaromatic and all those. Further, we have two higher order relation called fused structure, which determines when two structures are fused, and a definition of connected structures to determine whether two structures are connected. So this is a fused structure. Two benzene rings, these are fused because they have two common atoms between them. This is a connected structure. Sorry. Something like that. Now, coming down to GNNs deal with graph spaces. So every data instance that GNN deal with is a graph. For instance, I have shown here a simple illustration what I mean here. Let's say we're dealing with binary classification problem, and let's say the classification is just that whether the molecule is a fused molecule or not. So this is a graph which is a fused molecule. This is a fused molecule. So these are all positive, say. And red guys are guys who do not have any kind of fused structure. Okay. Now we define a graph G in that graph space a tuple of these 5 guys. V, which is a set of vertices, E is a subset of V cross B, a set of edges, and then we have a neighborhood function. Of course, we can get the neighborhood function from E, but explicitly we are providing here for simplicity. And then we have a vertex labeling function, psi. That means the GNNs really deal with graphs which are labeled. When we say graphs which are labeled, it means that the nodes and the edges of the graphs are labeled. So we have two leveling functions, vertex leveling function psi and edge leveling function epsilon. So one, for example, vertex labels are these. So the vertices V1 to V6 for this benzene ring are labeled. For example, we have this carbon atom, so we are labeling those as carbon atom. This is one particular kind of labeling. Someone can come up with some other kind of labeling as well. And then edge labels are epsilon of E1 and E2 of E3. These are all bonds, saying single bonds, and then E2, E4, E6 are double bonds. There is some error here. This should be 1. A GNN iteratively updates the graph labeling using something called a relabeling function. It updates the node label and the edge labels iteratively. So it takes the relabel function takes the graph VE sigma psi and epsilon, and it returns VE sigma psi dash and E epsilon. You notice clearly that the epsilon is not changed because in our implementation we are dealing with GNNs which only change the vertex labels. So this relabel function is in practice implemented using some kind of aggregate and combine procedure. So more on this can be read from our paper, so which are mainly graph convolution and graph pooling operations. Since we're concerned with graph classification, that is classifying each graph data instance as some class, so we need to convert the whole graph that we obtained after all this relabeling. We need to convert that into a real vector or some kind of some Boolean vector, whatever, some vector we need to convert such that we can straight away deal with that vector. So we call that as a graph representation, and that is done using a vectorized function. And that transforms the relabeled graph G dash and produces a real vector in D, a D-dimensional real vector. And this function in practice is implemented using a readout procedure, which are mainly global or hierarchical pooling operations. And then once you get that real vector, we can attach some kind of neural network that will take that input RD and returns the class label. And mainly in GNNs, that NN is essentially a multi-layered network, or we call that multi-layer perceptron, a fully connected feed-forward network. So now that we have formed the basis for data, background knowledge, and the model, we can straight away go to what we're interested in. So I'll skip over this Hagen slide. This is just prepared for my talks. Okay, so conclusion was that this idea of Hagen is a very simple idea, where what we used to do is we just, I'll quickly tell, what we used to do is the domain knowledge, the domain information of available in the background knowledge are just incorporated into the vertex labels. So initially, if you do not have domain knowledge, the GNN should be dealing with graphs like these, where the vertex level are just carbon, 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 and all that. Once we have the access to symbolic domain knowledge, what we used to do is we update the vertex level into this. So C vertex level becomes C, R1, C, R1, R2, depending on whether that particular atom is participating in any kind of any domain relation or not. So, for instance, the nodes 1, 2, 3, 4, 5, 6 are participating in this benzene ring. So they will get that label R1 because R1 is corresponding to that benzene ring. Similarly, whether they are participating in alcohol group, methyl group, or fused ring, based on that, we'll update the vertex label. So, and then this becomes the new graph, which we call a vertex enriched graph, and that goes as input to our GNN. It's a very simple idea, and it has been shown to perform very well, as you can see, as compared to our baseline GNNs. That is, baseline means that with the guy which has the GNNs which have no access to domain knowledge, as compared to those, we are able to perform very well across 73 data sets. And the results are very significant, as you see. Out of 73 data set, the Hagen we know in 48, 48, 53, 54, and 43 cases. And we have tested it across 5 different variants of GNN. So when I say it's a GNN variant, I mean the kind of implementation that involves graph convolution and pooling. And these are mainly the state-of-the-art GNNs that people use. So the experiment have been really large scale, dealing with 73 data set across 5 different variants and multiple hyperparameters. And also we have seen additionally that if you construct higher order IL relation using an ILP engine, even the performance can boosted more. So more on this can be found out in our paper, but I will not talk about that at this point.
Tirtharaj, what was the y-axis in the previous one?
Sorry, yeah, this is gain.
Right.
Gain means the as compared to the baseline GNN, how much gain we are achieving. A gain of greater than 1 is expected. So in few cases we definitely lose, but that's okay. Thank you. So code and the preprint is available. People can look at that later. Now coming down to the real talk that I was planning to give. This is bot GNNs. It uses the idea of more directed inverse entanglement, MDIE, which is developed, which is the core of inductive logic programming to incorporate first order domain knowledge into GNNs. Okay, so how are you doing that? Now, given a relational data instance E and some background knowledge B, MDIE identifies a most specific logic formula bot BE. Sorry for this notation, but these are convenient for us. So what it does is, if you recall the molecular graph structure, what we used to have is just atom or bond information. Now, if you are providing additional domain information such as existence of functional groups, rings, fused groups, connected structure, and all that, then MDIE identifies all those information related to this particular data instance E. And that helps us by to get a very nicely explained or an extended explanation of E. Then what we do is we propose a method that transforms that logical formula, bot E, into a bottom graph, a bipartite graph. And then a GNN straight away can deal with those bipartite graphs. I'll skip over this, but quickly I'll just tell. So background knowledge is set of concepts C1, C2, up to so many. Then examples consist of E plus and E minus, positive and negatives, and the hypothesis is H is equal to G1 convection G2.
Tirtharaj, Venkat has a question.
Yeah, sorry.
Yeah, sorry. I was just curious why it's called a bottom graph. I mean, is it related to the notion of a contradiction?
Yeah, I'll explain that. I'll explain.
Okay. All right.
Yeah. So there are some logical requirements when we're constructing this hypothesis H given this data and background knowledge. But I'll skip this. Prior necessity is that the background knowledge should not entail any of the positive example, because if that happens, there is nothing need to be learned. Main thing is this. We are interested in entailing all the positive examples. That means we are interested in finding a hypothesis that in conjunction with the background knowledge must entail all the positive examples. And what is inverse entailment? This idea of inverse. So from posterior necessity requirement, what we know is that the background knowledge and hypothesis combinedly should entail all the positives. So, but we do not know what this H is. So by the application of reduction theorem, what we get is that so B conjunction with E plus negated E plus would entail the negative H. So what that means, I'll come in a moment. I'll show you an example. Must be somewhere. Okay, so let's say this is our background knowledge. Parent X is a parent of Y. If X is father of Y, okay? And similarly, or it is a mother of Y. And we know, and also available is the fact that Jane is mother of Alice. And we are given, say, for example, an instance E, which says Henry is grandparent of John. So this is Henry, and this is Jane, and this is John. So Jane is mother of John, and Henry is a grandparent of John, because we have found the example tells that Jane is mother of John. Okay. Now, how does MPI combines these details or these relations available in B into E? So MTI points out that by doing so it takes into account the information available in B and then just makes a union of those. So what are the terms available here? Henry, John, and Jane. So it will try to take those terms and try to see what are the relations that can be found out from. So if we replace this X with say Henry and Y with John, whether this relation will be true or not. If it is true, then bring it to the description of B. Otherwise, not. So it will try to find all those relations in B which are found to be true for this particular example. So here, what we found is G parent and then father and mother was already there. What were not existing is this parent information. Parent Henry Jane, this should be Jane. Parent Henry Jane, parent Jane Alice, parent Jane John. So these are the three additional information that we could incorporate into this description of E. Now, that particular this particular set of ground atoms that we have obtained from B union E negated E can be written in a clausal form. That is, so a simple way of writing this is also can be written as a set, grandparent this, and then father, and then mother, and all that. So it can be a set. When you convert to another representation of representing the set as a clause is this, the negated guy becomes the head of the clause, and the other guy becomes the body. That is antecedent and consequent and antecedent. Okay, so what we have is the
Tirtharaj, what does the comma denote here? Comma is and, is
comma
it?
is and. Comma is and.
Okay.
Yeah. So if you look at this, sorry, I made a mistake there in the previous one. This should be actually since we are only these are the things which are B union E. To obtain the hypothesis, we need to take another negation, which will return this set. That means the positive guys who are there, they will become negative here, and the negative guys also will become positive. So what we get is the G parent, which is a positive literal, and the other guys are all negative literals. So this results in this clausal form. So the positive literals always appears in the head of the clause, and the negative literals appear in the body of the clause. Now, thing is that the practical issue is that given a very large background knowledge, this most specific clause. So this we call the most specific clause for this particular example. This could be very infinitely long. So it's practically sometimes infeasible to find a clause D that subsumes the bottom clause. So the idea of subsumption I cannot say because here I don't have the material to explain, but it's very difficult to find out a particular hypothesis for a very large B. So what we have is we need to impose some kind of restriction on this most specific clause. So we use it. So the idea is to use a constraint subset of definite clauses that to construct that bottom clause E. It's also called the bottom clause, by the way. I forgot to tell. What it does is it bounds the depth of the most specific clause. That is, if this was your say bottom clause B that you would have obtained with B and the data instance E, instead of finding out the most specific clause, try to find out a clause which subsumes this. So something like some guy over here. So also that means you put a depth bound on the bottom clause. So that means possibly a subset for this particular bottom clause, subset of this bottom clause. And that is done with the help of some language constraint on the definite clauses, and these are called mode declarations. I'll explain a few. So what are these? So for our grandparent example, the mode declarations are these. These are the language constraint on the definite clause. So the head has the mode declaration mode H, and the body literals have the declaration mode B. So for all the literals, we have these mode declarations. And what are these plus and minuses? The plus, minus, and or sometimes we'll have some hashes. They are variable that correspond to input or output variable, or sometimes some constants. And person means what type of variable we're dealing with. So Henry, John, Jane, Alice, these are all type person. Sometimes we may have types such as male, female, animal, all possible kind of types, depending on the kind of problem that we are dealing with. I'll skip this. So here I'm trying to illustrate the meaning of the depth D. So if your depth is equal to 1, so in this case, I told you that we need to find out a bottom clause at some particular depth D that could subsume the most specific clause. So if your D is equal to 1, then the variables that appear in this bottom clause, they must have, or the terms that appear in the clause must have maximum depth of D is equal to 1. So Henry has a depth of 0, John has a depth of 0, Jane has a depth of 1, and so on. So none of these variables, they have depth of more than 1. Similarly, if I'm imposing a depth of 2, that means the variables or the terms that appear in the body or the head, they must not have the depth greater than 2. So all of these terms have depth at most 2. Now that we now know what we are talking about, so that is a depth-bounded bottom clause. Now we need to see how to construct the body chain. Now steps are the following. Draw an instance E from the data set. We are given a data set of relational instances E. So when I say relational data instances, it could mean graphs, it could mean relational databases, it could mean any kind of relational form, knowledge graphs and all that. So then we need to transform that into some kind of prolog fact, but I'll keep this information later towards the end of this body and talk. Now, once you have drawn an example, saturate E with MDIE with the language constraint and set of modes M and the depth and all that, and obtain the output, the bottom B, M, D of that. Okay. So you have now this mode declaration and depth added to this bottom clause. These are the restrictions. Now we construct a bottom graph. I'll come to this in next slide, and repeat until all the examples in the data sets are saturated. Now the step 3, it requires an idea of matching mode and matching type. Let us see what that means. Now let us talk about the second, the bottom clause with depth 2 for the grandparent example. So for our literals in that grandparent example with the depth 2, we are showing here the literals in the clause and the corresponding modes which are matching to them. So we have these 7 literals. If you recall, the first was the head. This was the head, and the others were all body. Now each literal will be matched against the mode declarations. So the first literal will match against the mu1 mode, and the father literal will match with the mode B father plus person minus person, and so on. Mother will match mu3, and parents will all match the fourth mode declaration, mode B parent plus person minus person. Now, similarly, the ground terms, they will match against the type. So all these are a person type. If we had something else, animal or a dog, say Henry likes a dog, so in that case, it will go and match against the particular type, animal. So, but in this case, we have all these persons. So these are matched, all of these ground terms match persons. Now the bottom graph we construct is this following. So this is a bipartite graph, as you can see. On the left, we have the literal vertices, and on the right side, we have the terms vertices. And we have in bracket, what you are seeing are the vertex labels. Okay, so and the head is denoted with dot just for clarification. So the labels will be obtained from this pair, that is, we have this literal and the matching mode. So this pair will be transformed into a particular labeling that I'll talk in a moment. Similarly, we have this term and type pair. This will be converted into a particular node labeling. Now, thing is that this head information, that is G parent, Henry, John, this is all the information that is required to do the classification, but we are not interested in that. We are interested in incorporating the domain information into GNN. So we're not going to look at the head. We are going to behead this bottom graph and only deal with the description for description for the example. And the description for the example is only available in the body of the example. So now the beheaded version will look like this, so this is we call the antecedent graph. That is the graph that represents the antecedent of our bottom clause, or the depth-bounded bottom clause. It's still the same, just the head node is gone. Now the labeling, as I told you, that each of those pairs, this lambda mu pair or tau gamma pair, will have to be converted to a fixed length vector. And in this case, we proposed this idea of converting with 4 different functions. So at this point, this is not important what this f, rho, gamma, tau, and r are, but in the end, what we get is that for each pair, we get a particular node vector. Now, the final bottom graph, or the bot GNN graph, not the bottom graph, but the bot GNN graph that we get is the antecedent graph, which has been which has all the very nice node labels or the node vectors. And as you can see, these are on-directed. So the idea of making this graph, this bot GNN graph on-directed is, there are 2 reasons. One is that the GNN variants that we are using, they deal with on-directed graphs. The implementations deal with on-directed graphs. And the second important reason is that on-directed version allows easy exchange of information among nodes in the graph. Although it's for a bipartite graph, it may seem easy, but it allows quick travel of information, for instance, from this particular node to say X7 and so on. So this is a very this will help us, we believe, in our implementations. So what we did so far is that we were provided with the data in graph space. Then we had to convert them into a symbolic space say, this particular graph will be converted to some atom bond information like that, and this particular graph into this. And then what we did is we are given some symbolic space of background knowledge, say benzene ring, pyrrole ring, fused, and all that. So for each instance, we have this additional description we can obtain. Then MDIE will combine these and give a very nice large description for each of these relational data instance. And these guys are this bottom clauses or this symbolic space is then converted to a bipartite graph space. So GNN will deal with this bipartite graph space, which was not the case with Vegans, for example. The graph space was not changing in Vegan, but only the node level space was changing. So the results are again large scale. The experiments are conducted at large scale. We're dealing with 73 data sets obtained from NCI, National Cancer Institute, mainly some kind of bioactivity, classification of bioactivities. And number of GNN variants is again 5, similar to what we had in Vegans. And what we obtained is that BOD GNN is superior to baseline GNN. Baseline GNN again here means the GNNs without access to any additional symbolic domain relation. They have only bond information available. And as you can see, the gain plot in almost all the cases, BOD GNN is able to achieve higher performance than the baseline GNN. That it tells us that the incorporating symbolic domain relation into GNN helps significantly. And also what we saw is that BOD GNN is really superior to the simple idea of Vegan as well. So this work essentially outdates the result that we have in Vegan. And it is a very significant result, as you can see. The simple idea of Vegan, we're able to beat it by 54, 61, 55, and all that. And all results are statistically significant. So the conclusion is that the following: the BOD GNNs change the input graph space to a bipartite graph space, and it provides a it provides a principled way of incorporating domain knowledge into GNN. What does that mean? That means that if we are able to get examples in a relational form and we have access to symbolic knowledge, we can use this idea of MDIE and bottom graph conversion and the thing that we're showing here so far to directly deal with GNNs or directly incorporate those information into GNNs. So it is not just restricted to graph spaces. It can go to relational databases as well. And we saw that MDIE is really helpful in providing us this luxury of incorporating easily these additional domain relations for every instance. So the preprint and code are available at these links. Now the third work that results from this is an application of BOD GNN for molecule generation or target specific molecule generation. So we are concerned with problem where we want to generate new small molecules that could act as inhibitor of a biological target. And also there is limited prior information available for that particular target. And we want to investigate whether domain knowledge can assist in generating such molecules. Now, idea is the following. It is again a neurosymbolic architecture that we propose. It combines deep neural networks with inductive logic programming, and it allows the use of exploiting this whole idea of MDIA again to to incorporate those symbolic knowledge into the into molecule generation. Now, let us say we have molecule and their activities. So this is my molecule, and Y is some activity. So we treat this as some instances of random variable x comma y. So what we are interested in is that we want to draw instances from the conditional distribution. That is, given some activity y, say positive or negative or active or inactive, and some background knowledge b, we want to be able to sample new molecules. And we can sample new molecules if we could construct a distribution over those. Now what we do is we decompose the ideas from Bayes rule. We decompose dx given y comma b into dx given b and dy given x comma b. So one is a discriminator, another is a generator. And now that we have theoretically decomposed this, we need to approximate this distribution given data. And that can be done with the help of deep models and, of course, with the help of MGI. Let us see how to do that. So we're interested in this target problem. Well-studied problem. It's a very well-studied problem over the years in computational biology and chemistry. We're dealing with Janus kinase class of protein, and target protein is JAK2. And we deal with two different scenarios where no data on inhibitors are available for target JAK2. That means we do not have any idea of any inhibitors for JAK2 protein. And the second scenario is we have some information available for the JAK2 inhibitors in the form of homologous proteins. So JAK1, JAK3 are the type 2 are the homologous to JAK2 proteins. These are the some information on inhibitors for JAK2. Now, our system design, an ideal case is this, that X will be drawn from that. So we have this, if you recall, we had decomposed our intended distribution into two parts. One is dx given b, another is dy given x comma b. So X will be sampled from dx given b, and y is a class level or which will be sampled from dy given x comma b. And we have a key which says I want to sample or I want to generate molecules which are active. So y is equal to y means active, say, and not y would mean non-active or inactive. So in the end, what we output is that we're able to then sample X given active molecules if y is equal to y and the background knowledge B. Now, how do we approximate this distribution? So that is a theoretical case, what we showed here. But when we want to approximate this using neural nets. So we have this very nice generator discriminator combination, not adversarial, but instead collaborative in some sense. So we have a generator G1 that tries to generate acceptable molecules. And there is a discriminator which provides the class label for these acceptable molecules. And together, we get molecules from here. We get labels, class label from our from D, and then G2 deals with molecules along with their class label. It constructs a distribution for x comma y. Okay, and it is a conditional distribution because we know what these class labels are. Now, where does background knowledge coming into picture here? It is coming in two different ways. One is while constructing the generators. So this is our background knowledge BG, and it is used in both the construction of both these generators G1 and G2. And there is additional symbolic domain knowledge, which is BD, BD refers to background knowledge for the discriminator D, BD. So we have two different sets of domain knowledge available to us. Let us see each of these blocks, what they are doing. So the generator G1, its aim is to learn the distribution of smiles representation. This is a representation. It's a very simple representation for molecule. So I may be wrong, but say benzene can be represented as C, 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 something like that. I may be wrong really there, but it's a very it's mainly a string. It's a string of characters. It includes equal to, brackets, and so many other things, semicolons and all that. So this is a representation, and from this representation, we need to construct the generator. So for that, we use the data available in the Campbell database. It was 1.9 million molecules by June of 2021. We used it. And background knowledge for this is propositional. This is, I'm talking about BG here, if you recall the BG generator. And these are propositional, these are constraints on molecular properties. And what does that mean? Say, for example, the background knowledge could say the constant that the solubility should be less than this, toxicity should be something greater than that and that. And we have 3 to 4 such constraints available to us, and we need to import those constraints when we are constructing the generator G1. So for this, we use a very simple structure for deep model, which is LSTM-based BAE. LSTM because we are dealing with sequences, and BAE because we want to construct the distribution. It's a variational autoencoder. It takes the smile strings, roughly 1.7 because we use some of those for testing purpose, testing the BAE while training. So once you get the VAE, it's very difficult to straightaway import BG into VAE modeling. So what we do instead is we use BG as a filter, and once we get the smile string sampled from VAE, we impose this filter on them. If the molecules pass the filter, we call them acceptable molecules. So that means here we are able to construct D given X comma BG. D of X given BG. This is hat because this is approximated. Now the discriminator D, here it is used to obtain the labels for the acceptable molecules. In the previous case, we got our molecules, but we need to now know what their activities are, whether they are active or inactive. So for that, we need to use the discriminator. It learns the conditional class probability distribution D hat Y given X comma B. Data are again smile string, but it's a very complicated way of, we need to convert those into, since if you recall we're dealing with a discriminator which are bottom graph neural network, they have a very nice principled way of incorporating symbolic knowledge. So, but they deal with relational data instances. So the smile string, they need to be converted into some relational form, and we have some programs that does that. So it requires a transducer to convert to a relational representation. So transducer, it means the set of programs that we have to do this conversion. And the background knowledge is again the first order, which are mainly functional groups, rings, and some high order relations that we saw in BOTGNN. So what it gets is that we construct this. So this is the whole BOTGNN framework. Here it uses MDIE to get into the BOTGNN graphs, and those graphs can be used to construct the BORD-GNN, and then BORD-GNN could provide us the labels. Now, you may ask, okay, you told me here that for these acceptable molecules, we need to get only the labels from the BORD-GNN, but how did you construct discriminator? Yeah, so we constructed this with those JAK2 homologs. If you recall, we had some information available from JAK2 homologs, that is JAK1, JAK3, and type 2. So those are the molecules that we use to construct this BORD-GNN discriminator. And now that we have acceptable molecules, we can straight away pass those into this BORD-GNN and get their class labels. Now the third guy, or the third block, is G2. And G2 is a conditional, it's a generator to approximate the conditional distribution G of X given Y comma B. And data for this is that those JAK2 homologs plus we get our acceptable molecules labeled with BORD-GNN class label, right? So we construct our G2 with the help of these JAK2 homologs and the acceptable molecule with the BORD-GNN labels. Now, you may think, okay, but the domain knowledge is not straight away involved in this. Of course, it is involved because we have constructed BORD-GNN with the help of symbolic knowledge, those domain knowledge. So this class, this BORD-GNN labels has so much more information already incorporated from that. Now the model is again LSTM-based BA, but only difference is that the input is not just smile, rather smiles appended with the class label y is equal to 0 or y is equal to 1. So the VA gets a smile string appended with active or inactive. So this is my input to the VA. So we have roughly some 20,000 odd smile strings to construct this G2.
So Tirtharaj, you promised a half an hour talk. You're now at 1 hour.
I'll just quickly finish. I just have 3 slides more.
Okay.
Yes. Evaluation metrics are these. So we need to sample a bunch of molecules from these generators and try to see how many of those guys are acceptable. That is, acceptable are those which satisfy the BG constraint. That is, they satisfy the molecular properties that we are interested in. And then we were interested in seeing how many of those those M-test molecule are predicted to be active. I'll talk about the proxy model briefly. And we need to see how many of those in the M1 are similar to JAK2 inhibitors. So, and for this we use tiny meter coefficient of greater than 0.75. So these are the results. As you can see, just for the moment, do not look at the first two, column 2 and 3, just look at the last one. If we do not have any access to domain knowledge, if we sample just randomly 5,000 molecules, we get 2877 guys which are found to be satisfying the BG constraint, the molecular property constraint. However, the activities are found to be very bad. That is, only 34% of those are found to be active. Whereas, if we have access to domain information, in this case, we have bond information as domain information we are calling. We do not have access to additional domain relation like functional groups, rings, and all that, only bond info. In that case, the activity jumps from 0.34 to 0.43. And additionally, if we incorporate functional groups, rings, and other higher order relations, we get activities jumping to 0.47. Similarly, the similarities, as you can see, if you randomly draw molecules from KML database, you get 0, none of those satisfying the similarity constraint. That means it's total failure. if you have only, if you sample from G2 constructed with labels from bot gene and without the domain relation, we have 0.11. Similarly, we have, it jumps further if we have additional domain information available. So we have, these are some sample molecules that we have generated and some assessment by computational chemist. So our colleague or co-author, or Dr. Arijit Roy is a computational chemist, so he has provided us with this description. So this is a novel molecule. The activity is 9.12, similarity is 0.15, which is not similar to, so this molecule is not similar to the JAK2 molecules. These are additional, some other molecules which have higher activity. But interesting thing is that, as you can see, new scaffolds we're able to get new scaffolds in these molecules. So these are really novel, which have not been seen earlier. And this is a result, this is from the fact that we have been able to incorporate this additional relation into this kind of conditional generation of molecules. So here we provided a combination of generator and discriminator working in collaboration to generate target-specific molecule. And again, we're saying again that the inclusion of domain relation into such end-to-end neural system improves the generative models. In fact, the generator was also able to generate novel scaffold that were not seen earlier. So this is very interesting result, and we are still experimenting further on these on various other targets. Yeah, sorry for taking so long, but it's a long set of works. Any question? Okay. If there are no more questions, I'll stop the recording and see you in the next APPCAIR talk, I guess.
Thank you.
Thank you.